Alcohols are compounds that have a hydroxyl group attached to a carbon when there are no other heteroatoms attached to that carbon. So if, for instance, this were a carbonyl group, this would be a carboxylic acid, not an alcohol. They both have OH. But the alcohols are compounds that have an sp3 carbon here and nothing special in terms of heteroatoms, hydrogens or carbons. Phenols are very special alcohols. They have a six-membered ring of a type that we call aromatic, alternating single and double bonds in two resonance forms, which is often written simply as a circle to indicate that all of those bonds are equivalent. And the OH group is attached directly to that ring. So these are alcohols, and these are phenols, and they do share some similarities because they both have hydroxyl groups. Their differences are far greater than their similarities. They have rather different chemistries. Their ways to make them are dramatically different. But because they share some key similarities, they may be discussed together. And let's just take a look at the ways in which they're similar as an introduction to these compounds. Number one, both of these types of compounds undergo hydrogen bonding. And you already know that that affects solubilities. And it affects melting points and boiling points. Typically, there'll be higher melting points and boiling points because of the hydrogen bonding. These guys also are similar in that they undergo oxidation. But quite frankly, the oxidation reactions that they undergo are quite different. And we'll focus more on the oxidation of alcohols than phenols. These compounds act as acids, and it's a key property of the hydroxyl group. So it's a key property of alcohols and phenols. And in this context, the phenols are distinctly more acidic than the alcohols, and we'll talk about why that is. The hydrogen bonding that occurs between an alcohol or a phenol and water greatly increases the solubility of some alcohols and phenols in water. Not only can you get the hydrogen bonding with the oxygen in water, but the proton of water can hydrogen bond with the oxygen in the hydroxyl group. So hydrogen bonding can be extensive, increase the solubility of alcohols as well as phenols in water, in very polar solvents like methanol and ethanol, other alcohols. The larger the molecule, the less effect this has on the whole molecule, because the smaller the alcohol is as a piece of the whole molecule. So as the alkyl group here becomes larger, So the hydrogen bonding effects that one sees with water and phenols are more pronounced when there are more than one hydroxyl group, or there's one hydroxyl group with a small molecule. I mentioned that alcohols and phenols are subject to oxidation. The fact is slightly different. Not all alcohols are readily oxidized, but those that have a hydrogen attached to that carbon are. And the oxidation occurs to form a carbonyl group. In the case of phenols, the oxidation is somewhat more complicated. Let me give you an example. This phenol that has two hydroxyl groups is fairly readily oxidized to a compound called benzoquinone. And as you would surmise from looking up above, the product is a carbonyl group. But before you feel comfortable about knowing the oxidative chemistry of phenols, let me show you this. Phenol itself can be oxidized to make exactly the same compound. There's no oxygen on that carbon initially, and yet the product is this dicarbonyl compound. So the oxidation chemistry of phenols is interesting, biologically important. It has some commercial importance and some use in research, not as extensive as the oxidation chemistry of alcohols. But it's also complicated, and the reagents used can be complicated. And we will simply be satisfied with the knowledge that phenols undergo oxidation readily, but perhaps in complicated ways. The most important practical use that I'm aware of is the fact that these compounds undergo radical oxidation readily and are therefore used as antioxidants. And that can be an important biological consequence as well as a chemical consequence. So the oxidation of alcohols and phenols occurs typically under different conditions, typically with different reagents. The oxidation of alcohols is widely used in research and commercially. If there's no hydrogen attached to this carbon that has a hydroxyl group, those molecules do not undergo oxidation under the same conditions, and it is well behaved away. So we will limit ourselves to thinking of this oxidative chemistry as the chemistry of methanol, primary alcohols, and secondary alcohols. Primary alcohols are those that have one alkyl group attached to this carbon. Secondary alcohols are those that have two alkyl groups attached to this carbon. The third characteristic of alcohols and phenols, shared by the two hydroxyl functionalities, is their behavior as acids and bases. We don't spend a lot of time talking about the behavior as a base of alcohols and phenols, especially phenols, but it is important, and it simply is a reflection that The hydroxyl group has an oxygen that has two unshared pairs of electrons. And a pair of electrons can be used to form a bond with a proton of an acidic substance, where that pair of electrons then stays with the conjugate base. In a reaction, it definitely is in equilibrium. And this equilibrium is something that we've seen a couple of times over when we've talked about the chemistry that leads to elimination and the chemistry that leads to substitution. Because you probably recall that this is a very poor leaving group. But this is a good leaving group. So we have seen this acid-base chemistry of the hydroxyl group in the context of substitution reactions and elimination reactions to make alkenes. The difference between alcohols and phenols is the aromatic compounds, even when they have good leaving groups, do not undergo that SN1 type of chemistry to form carbocations there, as we saw for elimination and substitution reactions. So this would be limited to alcohols. Not phenols. But of course, both act as bases. It's simply that the protonated phenols don't undergo the substitution or elimination subsequent chemistry that is typical of the alcohols. So I'll say alcohol or phenol. Undergoes this kind of chemistry. The chemistry that alcohols and phenols share in common, acting as acids, I'm going to put a negative charge on that base. And all bases have a pair of electrons to share with a proton. And that bond between the O and the H cleaves to make an alkoxyanion, often known as an alkoxide. Or phenoxide. And then the question that often comes up is the issue of relative acidities. And let me ask you for just a minute. Of the alcohols and phenols, comparing those two, which do you think is more acidic? What do you need to think about when you're determining relative acidity? The most important factor is the relative stabilities of the conjugate bases. So these relative acidities are determined by the relative stabilities of the conjugate bases. And so what are the factors here? Well, let me just give you the facts and then we can explain them. Water pKa is 15.7. The pKa of ethanol just 16.0 according to Klein's textbook, while phenol let me write it this way, is 9.9. These are very similar. Much more acidic. In fact, because this is a log scale, it's about 10 to the 6th times more acidic than a simple alcohol like ethanol or water. What do these data mean for equilibrium and its effect on our chemical thinking? Well, let's take a look at these equilibria. These data tell us that if we put a primary alcohol together with a base like sodium hydroxide, the resulting equilibrium will have considerable amounts of both acids, because this acid, pKa, let's say of 16, this has a pKa 15.7. This is stronger because it's smaller, but not by a lot. So this equilibrium will be shifted in this direction slightly. Conclusion is using NaOH is a poor way not an effective reagent. To make alkoxides. We'll need a much stronger base. We could think of several, but there are two ways to make these alkoxides that exploit a trick to drive the equilibrium to fully prepare the alkoxide. One is use sodium hydride. It's a very strong base, and the product is hydrogen gas, which is evolved. So this is an acid-base reaction. It's driven entirely to the right. There is no equilibrium to the left. The second way alkoxides are made is to use sodium. And sodium metal reacts with alcohols. And the product again is hydrogen. This is an oxidation reduction reaction. So I'm going to say reduction because we're reducing the organic compound. And it also is irreversible. So for synthetic preparation of alkoxides, these are the two common methods. For phenols, it's a different story. When phenols are treated with sodium hydroxide, an equilibrium is established. Where again we make the conjugate base of the alcohol, or phenol, plus water. And now we see that pKa is 9.9 and 15.7. This is much stronger. Stronger pushes to weaker in acid-base equilibrium. So this equilibrium is dramatically shifted to the right. And sodium hydroxide is an effective reagent. So, bottom line, alcohols and water are of similar acidity, and it takes a very strong base, something very different from sodium hydroxide, to make alkoxides. On the other hand, phenols are much more acidic than alcohols because the conjugate base is much more stable than an alkoxide. And so sodium hydroxide is an effective reagent for making a phenoxide. So that's a quick overview of the chemistry of the alcohols and phenols, where they are similar. Their acid-base chemistry is similar. Both types of compounds are subject to oxidation, but the actual oxidation chemistry is quite different. And hydrogen bonding is a significant factor in the solubility and melting and boiling point properties of alcohols and phenols, especially small alcohols and small phenols.